Now let's look at a beam element and try to solve for the safe functions of its degrees of freedoms. Let's say we have a beam here like this, and there are two nodes, one here and the second one here. As you know that beams will have 2 degrees of freedom at each node, and there will be the displacements in the vertical direction and anticlockwise rotations as well. Now you see here that there are 4 degrees of freedoms, which means that if we use 4 boundary conditions which we have, we can solve for 4 unknowns. And this is a 1D problem. So here this is direction x and this is the displacement u. Now this beam under certain loading may deflect like this. Now for this case, we are interested to find the displacement at, say, a certain point like here at x distance from this end. So let this be 0, this be L. So we want to find what is the displacement here, ux. Now what to do is, if the exact solution of this one be something like this, we're not sure, and we are approximating its solution by a certain curve, which is the green one, we assume this green to be our safe function or our assumed or approximate deflected shape, which will be given by a certain equation. Now, since there are 4 boundary conditions, we can have an equation which has 4 unknowns. Let this be like this. So this can be our equation in cubical form. This is similar to the one we did in bar element. Now in the bar element, we only had 2 degrees of freedoms. Therefore, we only had this part here. And we had to solve for A0 and A1. Now here, since we have 4 degrees of freedoms, we solve for 4 of them. Now, what I have to look into is the boundary conditions. Now the first boundary condition here, now this is x, and we have this is x at 0, this is x at L. So your first boundary condition is that your u displacement at 0 equals to u1, which is the vertical displacement. Now this is ux, this equals to u1. Now if you plug 0 in this equation, what you get is this equals to A0. That's our first equation. Now the second boundary condition is we have slope at 0, which is u2. Now this one will be equal to, now if you differentiate this equation by x and plug in 0, now what you'll get is you'll have a1 plus a2 2a2x plus 3a3 x squared. Now if you put this one 0 and this one 0, you'll get a1. So u2 will be equals to a1, or a1 will be equals to u2. Now the third boundary condition is u at L equals to u3. Now if you substitute L here, then what you get is a0 plus a1L plus a2L square plus a3L cube. That's our third equation. Now the fourth one is the slope at L, that equals to u4, that equals to a1 plus 2a2L plus 3a3L square. This is our fourth equation. Please remember that we have already solved for these values, so these are all known under the loading condition. Now here we have to solve for a0, a1, a2 and a3. Now to do this, there are two methods. You can solve them by substituting the values, or you can do it by matrix method. Now for this one, what to do is we substitute the values of a0 and a1 into these equations and solve for u3 and u4. Now while doing this, what you'll get is you'll get your u3 as, and your a4 will be equal to. Now once you have this, you can plug your a0, a1, a2 and a3 back into this equation here, and you can write your solution. Now your solution will look something like, now this will be your solution. Now this is in form n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. See, we have 4 degrees of freedom, therefore we'll have 4 shape functions for each of the degrees of freedom. And you can substitute your x by L by S and write your solution in form of S, where S varies from 0 to 1, or you can substitute your S by xi plus 1 by 2, and you can have your solution in terms of xi, which is a natural coordinate. Now your xi varies from -1 to 1. Now the other method is to use the matrix. So when you write this equation in matrix form, you'll get u vector equals to 1 x square x cube times of a0, a1, a2 and a3. Now you have to solve for this vector here. Now these boundary condition equations can also be written in matrix form. Now you can solve for this by taking this matrix on this side and taking its inverse. Now when you do this, and then when you substitute your a0 back here, then you can write your solution in this form. You will have u vector, which will be your solution. You can write x here, and it will be n1, n2, n3, n4, and then u1, u2, u3, u4, and these n values will correspond to these values here. Now if this is in x, means that these all will be in x as well. Now if you write this in xi form, you will have n1 as a function of xi, n2 as a function of xi, n3 as a function of xi, and n4 as a function of xi. And then you'll have u1, u2, u3 and u4. Now when you write this in form of xi, you can get a simpler form as your n1 as a function of xi equals to 2 minus 3 xi plus xi cubed by 4. Your n2 xi equals to 1 minus xi square plus xi cube times L by 8. Your n3 xi will be equals to 2 plus 3 xi minus xi cube divided by 4, and then your n4 xi will be equal to minus 1 minus xi plus xi square plus xi cube times L by 8. So this will be your shape functions in terms of xi. And let's check our validity of shape function n1. your n1 at 1, that is, in your xy coordinate system, this is -1 and this is 0. So your n1 at 1, which is -1, should be equal to 1. Let's see. So it will be 2 plus 3 minus 1 divided by 4. This equals to 5 minus 4, that is 4 by 4 equals to 1. And your n1 at other coordinate system must be equals to 0. You can check these properties for all the other degrees of freedom as well. Now here you can see that these values here, when you add them up, may not be equal to 1. Let's try adding them up. Let's see. So here they don't add up to 1 because we are looking into different degrees of freedom in different directions. Now this one is rotation, this is vertical displacements. That's why they don't add up to 1. Therefore be careful not to use this property of safe function that equal to 1 while using the beam element. Now these functions in terms of xi, these ones here, are known as Hermite polynomials. So now let us try to solve for the safe functions for 2D elements. The 2D elements can be triangle or can be rectangles or maybe any other shapes, but these are generally common shapes because they allow faster processing in the finite element analysis programs. Now here these elements can have 3 nodes, 6 nodes or 7 nodes. Here this one can have 4 nodes or 8 nodes, 9 nodes or many more. If you have an element like this and we solve for each of the nodes here, and then we'd like to find what is the solution here, what is the displacement here, which will be a function of x or y. Here also we want to find the displacement at this point. Let this be ux, y. Now to do this, we also have to define the shape functions. We have to look into Pascal's triangle, which provides us a way of choosing the approximate shape functions. Now this triangle looks something like this. You may have already seen in your textbooks. This is 1D as a function of x. This is also 1D as a function of the area here is function of both x and y, which is a 2D xy. Now what you'll see there is you'll have 1 here and xy, x square xy y square, x cube x square y, xy square y cube y4, and so on. If you want to choose a polynomial that is in 2D, let's say that is in 1D as a function of x, you can see here that for an axial member you'll only choose this part here as a function of x. So you'll have 2 terms for a bar element, which will be a0 plus a1x. Now if you're also looking at a 1D element like we did for the beam, you can see here that there are 4 degrees of freedom. So we can choose up to here. This will have 4 terms for beam, and this will look something like a0 plus a1x plus a2x squared plus a3x cubed up to here. Similarly, you can do it for the y-axis as well. Now for a 2D element, if we say that we are looking at a rectangular element which has 4 nodes, then we are looking for 4 terms. Now here, up to here, it's 1, x and y, that's 3 terms. But if you look at this one, if you add this up, then you'll have 1, 2, 3, 4, 5, 6 terms. Let's take that one out. So you'll see that your displacement as a function of x and y, so you have 6 unknowns. So you need 6 boundary conditions or 6 nodes to solve them. But you don't have it, we only have 4. So what to do here is, generally we can neglect the higher order terms. So we can neglect this one and this one. So what you have here is, you'll get a0 plus a1x plus a2y plus a4x y. Now you see you have 4 terms here and you have 4 nodes. Therefore you can use this function to solve for your shape function. Let's try this. Now let's take a rectangular element which has 4 nodes. Let this be node A, B, C and D. Now you see, either we can do this in x and y, or you can do this in natural coordinates. Now here generally we use natural coordinates. Now since this is a 2D plate, what you'll have is one coordinate in this direction and you'll have another natural coordinate in the y direction. Now you can assume this to be the origin. So if this is 0, 0, then you see that this point here we can take as -1, -1. This will be 1, -1. This will be 1, 1, and this will be -1, 1. Because your xi, this is xi axis, this is your eta axis, your xi varies from -1 to 1, and your eta will also vary from -1 to 1. Now these will be your coordinates of the nodes. At these nodes, we already have found our solution in the x and y direction. Now let our solution u as a function of xi and eta be of this form here. Now in terms of x, we write xi. In terms of y, we write eta. Now I can write this in matrix form. You will have your u. Now let's say your solutions at these points are u1, u2, u3 and u4. Then we apply the boundary conditions. So what we'll get is, if you look at A, where xi equals to -1 and eta equals to -1, you will have u -1 -1, which will be equals to u1 will be equal to, similarly, now you can write this in the matrix form. Now from here you can solve for this, and then you'll have your u1, u2, u3 and u4. And this is your solution for the coefficients. You can substitute this back into this equation here, and then what you'll get is times your displacement vector. Now you can write this in this form: n1, n2, n3 and n4 times of u vector. Therefore, when you compare this, what you'll get is by 4. So you can see here that we have found our shape functions for the 4 nodes. Now you can verify the shape functions by its properties. Now when you say that n1 at the rate 1, which is xi equals to -1, eta equals to -1, should be equals to 1. When you substitute those values, what you get is 1 plus 1, 1 plus 1 by 4, that equals to 1. And your n1 at the rate 2, 3 and 4 must be equals to 0. And probably when you add these up, you'll also get a summation of ni will be equals to 1 as well. So this is how you solve for the shape functions of a 2D element with 4 nodes. Now the question arises, like when you have a rectangle like this. Let's say it has 1, 2, 3, 4, 5, 6, 7 and 8 nodes. What do you do then? So for this, we have to look into the concept of Lagrangian polynomials, or concept of serendipity elements.